Hello, welcome to the fair clustering tutorial. So here's the outline of the tutorial. We'll begin by discussing some clustering paradigms plus a short introduction to algorithmic fairness and how it factors in clustering. Then we'll talk about demographic or group fairness in clustering. Then we'll talk about individual fairness in clustering. Then we'll talk about algorithmic aspects in fair clustering. Specifically, we will talk about the two-stage approach for solving fair clustering problems, which is an approach that has been successful in solving a collection of fair clustering variants. And finally, we will talk about overlooked issues in fair clustering. Alright, so let's start with the clustering paradigms. So first, let's begin with the motivation for clustering. So clustering has a motivation from machine learning and data analysis. Specifically, we would have a collection of points and we would want to explore the data. We would want to reveal the existing structure and group similar points to one another. Indeed, we have this quote from Van Luxburg, which says, in virtually every scientific field dealing with empirical data, people attempt to get a first impression on their data by trying to identify groups of similar behavior in their data. So, given the following set of points, we can clearly see that we have 4 clusters. We might apply a clustering algorithm with k equal to 4, such as the k-means, and we would end up with the following clustering. And, this is an illustrative example. In a real application, the data will exist in a high-dimensional space, and it wouldn't be easy to see them visually, see the clustering visually, and, clustering algorithm would in fact give us the clustering, the partitioning of the data points into clusters. Another motivation for clustering is operations research. Specifically, we would want to allocate a collection of facilities or fire stations to serve a collection of users. So we would want to allocate those facilities in such a way that we minimize the travel distance between the facilities and the users. So, for example, if we're given the following set of locations, we can cluster with k equal to 2, where we basically place fire stations in this manner, minimizing the distance between the users and the fire stations. Alright, now let's go through the clustering paradigms. We will discuss the following 4 paradigms: center-based clustering, which includes k-means, k-median, and k-center clustering. Then we will talk about spectral clustering. Then we'll move to correlation clustering. And finally, we will talk about hierarchical clustering. So let's begin with center-based clustering. So in center-based clustering, the clustering is decided by choosing k-centers. And simply once the centers have been chosen, we just go ahead and assign each point to its closest center. Center-based clustering includes familiar and famous examples such as the k-means, the k-median, and the k-center clustering. Now let's formalize center-based clustering. So the input is a set of points C. Then we have for every two points I and j and C, we have a distance function d of I and j. And d of I and j is basically a metric. That means it satisfies the properties of the metric. That is, d of I and j should be non-negative. It's equal to 0 if and only if I equals j. That is the distance between the point and itself. And it should satisfy the triangle inequality as well as being symmetric. So d of I and j equals d of j and I. And we're also given the number of clusters, k, that decides the number of partitionings that we should have at the end, the number of clusters. And the output should be the following. So we should output the set of centers S, where the cardinality of S should not exceed k. And we should also output the assignment function, where the assignment function simply assigns points in C to the centers S. And it's clear that once we decide the set of centers, once we decide the assigned function, we basically have a partitioning, a clustering. We have basically k groups. Alright, let's formalize the center-based clustering objectives that we have. So we'll keep in mind that d of j and phi of j is the distance between point j and its assigned center. So the k-center objective minimizes the maximal distance between a point and its assigned center. So this is the minimum of the maximum across the points of the distance between a point and its assigned center. And you can see that the k-center objective is sensitive to outliers. So for example, given K-center clustering over a dataset, the addition of outliers could actually significantly change the clustering if you apply K-center, because K-center looks at the maximum distance between a point and its center. The K-median objective, on the other hand, minimizes the sum of the distances between the points and their assigned center. So, unlike the K-center, the K-median is basically aggregating the distances instead of just minimizing the maximum, and as a result, the K-median is basically more noise tolerant. You can tell because of the aggregation. The K-means is sort of like the K-median, but instead of minimizing the distance, we minimize the square of the distance, and as a result, the K-means is roughly between the K-median and the K-center objective in terms of its sensitivity to outliers. The square of taking the square basically makes large values even larger, and as a result, the K-means is more sensitive to outliers than the K-median, but it's not as sensitive to outliers as the K-center because it basically aggregates instead of looking at the maximum distance. All of the center-based clustering objectives can in fact be written in one unified form. So specifically, if we basically form a vector where the first entry is the distance between the first point and its assigned center, the second entry is the distance between the second point and its assigned center, and so on. Now if we take these values, stack them up in a vector, then the different clustering objectives just correspond to taking different p-norms of the vector. So when we take the infinity norm, we get the K-center objective. When we take the 1 norm, we get the K-median objective. And when we take the 2 norm, we get the K-means objective. Now, we spoke about the assignment function, which assigns points to centers. In fact, it may seem unnecessary because, as we said, each point is simply assigned to its closest centers. And this is in fact true. So, in the absence of constraints, the assignment function phi is trivial. Simply, we assign each point to its nearest center. So, for example, if we have this input, these collection of points, and we were doing clustering with k equal to 2, then we would get the following clustering. So, x denotes a center, so we have a center here, we have a center there, and we have the following cluster on the right and this cluster on the left, and clearly each point is assigned to its closest center. Now, when constraints are imposed in clustering, the assignment actually becomes non-trivial. So, given the same set of points, let's now impose the constraint where we say we should have at least 3 points in each cluster. Now, clearly the cluster on the right has an issue because it only has 2 points and it needs a third one to satisfy the constraint of having at least 3 points. So we'd actually end up with the following clustering, where clearly this point right here has been assigned to a center which is not its nearest center. It's been assigned to the center of the right instead of being assigned to the center on the left. But this had to be done in order to satisfy the constraint of having at least 3 points. This observation is in fact important because most fair clustering problems are actually clustering problems subject to a fairness constraint. So if we're doing center-based clustering, we would actually expect this behavior. So the assignment function generally in fair clustering is not trivial, and we cannot just assign a point to its closest center. Rather, we have to assign it in such a way that we minimize the clustering objective and also satisfy the fairness constraint. Now let's talk about spectral clustering. So in spectral clustering, we have the points that were given are basically vertices in a graph, and for every point I and j, for every pair I and j, we have an edge between them, and the weight of the edge wij indicates the similarity between I and j, and wij is non-negative. So we could be given the following example, where we have a collection of vertices, and the thickness of the edge indicates the value of the weight. So a thick edge is a large weight, and thin edges basically have small weight, and we can clearly see that the group of 3 red vertices have a high connection between them. The weight of the connections between them is large. So and that's also the case for the group vertices and for the blue vertices and for the green vertices. However, the connections between different groups have a low weight, as indicated by the thin edges. And you might think that maybe a plausible way to cluster such a graph is to just group the points which have high connections and basically separate separate groups which have small connections between them. So we would separate the red group from the blue, and we would also separate the green from the red and the blue. And in fact, that's basically what we try to do in spectral clustering. So spectral clustering partitions the graph so that edges between points in different clusters have low weight. And from this description, we can say that we have a graph cut problem. So let's be more precise. Let's say that we have the following graph with the subgraph A on the left and the subgraph B on the right. The cut between A and B is the sum of the weights between A and B, the sum of the weights of the edges connecting A and B. So if we wanted to calculate the cut between A and B, then we would simply sum the weights along the edges which connect A and B, and that's basically the sum of the weights of the blue edges shown. So what is the formal definition of spectral clustering? We're given a graph G, and we're also given a number of clusters K, and we want to partition V into a collection of clusters where we minimize the following objective function. We want to minimize the sum of the cut between the partition Ci and the rest of the graph divided by the size of Ci, and we sum that across the partitions. So what is exactly the size of Ci? So Ci, there are two ways to basically take the size of Ci. One definition is that the size of Ci is equal to the cardinality of Ci, that is the number of vertices in Ci. And if we take this definition, we basically get the ratio cut, where it's again the same definition, just where the size is measured by the number of points in Ci. Another definition is that the size of Ci is equal to the sum of the degrees of the points in Ci, where degree here has a weighted notion. So basically, for a point j, dj is equal to the sum of the weights between j and the rest of the points j prime in the graph. And if we take this as a measure of size, then we get the normalized cut, where it's basically, again, the same definition, the sum from I equals 1 to k of the cuts between Ci, the rest of the graph, divided by the size of Ci. Now, let's talk about correlation clustering. Similar to spectral clustering, we can think of the points as being in a graph, but here every I and j has two sets of values, wij plus and wij minus, both of them being non-negative. Wij plus is the degree to which I and j are similar, and wij minus is the degree to which I and j are different or dissimilar. And you can now sort of think of a clustering objective. We basically want to cluster the points in such a way that the points within the same cluster have large wij plus value, and the points in different clusters have large wij minus value, that is, they're dissimilar. In fact, that's what we're trying to do. So we want to cluster, partition the graph so that you get large wij plus within the cluster and large wij minus, large dissimilarity between different clusters. And formally, this basically leads to the following objective. So given a graph G, we want to partition it into C1 up to Ck in such a way that we maximize the following objective. So maximize wij plus between I and j in the same cluster, plus wij minus between I and j in different clusters. And what is interesting to point out is that the number of clusters K is actually not given as an input. So in correlation clustering, you actually don't have to give the number of clusters as an input, and this can be seen as an advantage because you don't have to figure out the number of clusters or try different values for K until you get a satisfying output. Now let's move to hierarchical clustering. So like correlation clustering, you don't need to set K, the number of clusters, but the output in hierarchical clustering is supposed to be basically a tree, or what they call a dendrogram. So points should be grouped together in a tree, and the higher you move up in the tree, the more points you're clustering. So let's consider the following example. So we have the following set of points, and the closer the points are to one another, the more similar they are to one another. So this pair of points is very similar to one another. How would hierarchical clustering look if we applied it to this following set of points? We would get something like this. So we would take the two points on the left, and we would group them with one another. We would take these 2 points, we would also cluster them, group them with one another, and then we would take these 2 clusters and then group them again. And similarly, we would do the same thing on the right, and then finally we can group the 2 clusters up, and that's basically the top of the tree, that's the root of the tree. And this is how the output of a hierarchical clustering looks like, with the root of the tree including all of the points in the data set, and the leaves of the tree including individual data points. One of the traditional ways to do hierarchical clustering is agglomerative clustering. In agglomerative clustering, you basically take 2 points and you group them together based on their similarity. Now, once you form clusters, you again merge the clusters based on their similarity. So it's a bottom-up approach where you basically grow the tree starting from the points that are similar, then the clusters which are similar, and so on. The problem with agglomerative clustering is that it does not include an optimization objective. So in the previous clustering paradigms, the center-based clustering such as k-means, k-median, and k-center, and spectral clustering and correlation clustering, we always had an objective function which we were either minimizing or maximizing. But in the case of agglomerative clustering, we don't have an objective function. Instead, the clustering is really defined through the operation of the algorithm. And this makes things ambiguous because you can imagine another algorithm which is also doing hierarchical clustering, and it would not be easy to compare it. So if you had an objective which you were optimizing, you can clearly compare different algorithms in terms of how they achieve the objectives, in terms of how they approximate the objective, and the algorithm which better approximates the objective could be considered to have a better performance. In fact, so the work of Dasgupta in 2016 basically defines a cost function for hierarchical clustering. We will not go into the details of that paper, but basically given a graph G with Wij specifying the similarity between points I and j, the objective function is the minimum of the sum of I and j times the similarity Wi of the similarity Wi and j multiplied by the number of descendants of the lowest common ancestor of I and j, which means that this objective places a higher penalty on separating points higher up in the tree because the number of descendants would be larger. There are also other objectives since that work which had been introduced for hierarchical clustering. The point is that basically we will follow the cost function approach to hierarchical clustering instead of agglomerative clustering. So we have a clear objective function which we're minimizing, just like the other clustering paradigms. Okay, so these are the clustering paradigms which we spoke about: the center-based, the spectral, the correlation, and the hierarchical clustering. Now, it turns out that all of them are actually NP-hard, and because they're NP-hard, we would not try to solve them optimally in polynomial time. Rather, if the minimum objective value is opt, then we would solve for opt hat, where opt hat is at most alpha times opt. So opt hat is basically not the optimal value, rather an approximation of the optimal value, and opt hat is also a bounded distance away from the opt. So it's at most alpha times opt. Alpha is called the approximation ratio. Clearly alpha has to be strictly greater than 1, since if alpha is equal to 1, then we have solved the problem exactly. And smaller values of alpha mean that we have a more accurate approximation. Okay, now let's move to algorithmic fairness. So now much of decision making is done at least partly using algorithms. And there are many examples, such as, for example, loan approval, recidivism prediction, and healthcare, where algorithms are applied in serious problems such as allocating limited resources and kidney exchange. Now, because of the widespread of algorithms, we have actually documented cases of algorithmic bias. We will not go through the examples, but we have basically books published about the topic. Because of this, we have substantial progress and interest in algorithmic fairness. So now let's think of some considerations for fairness when doing clustering. So For a point I, its distance from the center is d of I and phi of I. Generally, every point wants to be close to the center, and this is motivated from both perspectives, machine learning and operations research. So if the point is closer to its center from a machine learning perspective, then it's better represented by the center. So the centers are mostly thought of as a summary or exemplars of the dataset, and therefore, if the point is closer to the center, then it's better represented by the center. In operations research, the distance to the center basically corresponds to the travel distance to the facility. The closer the center, the less the travel distance. So points want to be closer to the center. Now, if we just consider this, we might think of an algorithm which violates a notion of fairness unintentionally. For example, we might do clustering, but we find that a group or demographic, a collection of points which belong to the same demographic, lie at the edge of the cluster, that is, they're consistently far away from the center. Such a group would basically be receiving a service of a low quality in comparison to other groups, possibly, and that might violate a notion of fairness. Another thing to think about in clustering is that clustering partitions the set of points into a collection of clusters, so C1 up to Ck. Different clusters will be processed differently. They will receive different outcomes and possibly different allocations. So let's say that we were doing clustering over this dataset where different colors indicate different demographics. So we have two demographics, red and blue. Now if we do clustering with k equal to 2, we probably end up with the following clustering, where the cluster C1 consists of entirely the blue demographic, whereas cluster C2 consists entirely of the red demographic. Now clearly any post-processing over the clusters might lead to whatever happens to C2 may not happen to C1 and vice versa. And since C2 is entirely red and C1 is entirely blue, then the demographics are not likely to enjoy the same outcome, and this might violate a notion of fairness. Similarly, we can also think about another notion. So points which are close to one another might desire the same treatment. So let's consider the following set of points. We have this cluster on the left, similarly this cluster on the right, and midway in between them we have these 2 points. Now if we cluster them, we might get the following output. Now clearly these 2 points are close to one another, but they have been assigned to different clusters. The one on the right is in C2, whereas the one on the left is in C1, and therefore they will basically likely enjoy different outcomes. And this may be an undesirable property, the separation of points which are close to one another. So for example, in a redistricting application, you might want to preserve community cohesion. You might not want to separate vertices which are close to one another. So that might also violate a notion of fairness. Thank you for listening, and now we will discuss demographic fairness in clustering.